Imagine if you could time travel to any point in the past or future. Fascinating, right? But according to the second law of thermodynamics, it's impossible. Welcome to the intriguing world of thermodynamics. Thermodynamics, from the Greek words thermi, meaning heat, and dynamos, meaning power, is a branch of physics that deals with heat and temperature, and their relation to energy, work, radiation, and properties of matter. It's a science that's been around since the early 19th century, when engineers were attempting to increase the efficiency of steam engines. Little did they know, their work would lay the foundation for a field of study that would revolutionize our understanding of the universe. Thermodynamics isn't just about steam engines, though. It's a fundamental part of our everyday lives. From how your refrigerator keeps your food cool, to how the sun warms our planet, these phenomena can all be explained by the principles of thermodynamics. It's also essential in numerous scientific and engineering disciplines such as chemical engineering, mechanical engineering, and even aerospace engineering. The key principles of thermodynamics are often expressed in the form of laws. The Zeroth law, for instance, introduces the concept of temperature. The first law, also known as the law of energy conservation, states that energy cannot be created or destroyed, only transferred or transformed. The second law, arguably the most famous, introduces the concept of entropy, suggesting that the universe tends towards disorder. And the third law, well, it's a bit more complicated, but it essentially states that nothing can reach absolute zero. These laws, along with the concepts of heat, work, internal energy, and entropy, form the bedrock of thermodynamics. They help us understand the behavior of the universe at a fundamental level and provide the basis for technological advances that have shaped our world. Thus, thermodynamics forms the backbone of many scientific and engineering principles. Now let's delve into the heart of thermodynamics by understanding its systems and properties. Imagine the universe as a gigantic stage where countless interactions and transformations of matter and energy take place. These interactions are governed by certain laws and principles, the rules of our game, so to speak. Within this vast stage, the actors that play out these fascinating dramas are what we call thermodynamic systems. Thermodynamic systems can be categorized into three main types: closed, open, and isolated. Closed systems can exchange energy but not matter with their surroundings. Open systems, on the other hand, can exchange both energy and matter. Isolated systems are the hermits of the thermodynamic world, as they exchange neither energy nor matter with their surroundings. These systems are characterized by certain properties, such as pressure, volume, and temperature. These are known as state variables because they describe the state of the system at any given moment. But these aren't the only players on our stage. There are others like enthalpy, entropy, and internal energy, which add more depth to the story. The relationships between these state variables are described by state equations. These equations are like the scripts that guide the performance of our actors, dictating how they interact with each other and their surroundings. State diagrams, on the other hand, are like the maps of our thermodynamic landscapes. They help us visualize the journey of a system as it moves from one state to another, allowing us to see the paths it can take and the transformations it can undergo. Understanding thermodynamic systems and their properties is like learning the language of the universe. It allows us to predict how energy and matter will behave under different conditions and to harness these behaviors for our benefit. So these systems and properties govern the physical and chemical behavior of matter and energy. Energy can neither be created nor destroyed, only transformed. This is the essence of the first law of thermodynamics. Now, what does this mean? Imagine you're pushing a heavy box across a room. You exert force and the box moves. You've done work. But where does that energy go? It doesn't disappear into thin air. Instead, it transforms into other forms of energy, like kinetic energy of the moving box and heat, due to the friction between the box and the floor. This is the principle of conservation of energy, a cornerstone of the first law of thermodynamics. Let's delve a bit deeper. Every system, whether it's our box, a steam engine, or the entire universe, has a certain amount of energy stored within it known as internal energy. This energy can be shifted around, transformed, but never created or destroyed. It's like having a fixed amount of money in your bank account. You can spend it on different things, save it, or even invest it. But you can't simply conjure more money out of thin air. Heat transfer is another crucial aspect of the first law. Going back to our box example, as you push the box, your muscles burn energy, warming you up. That's heat transfer. the movement of energy from a hotter object to a cooler one. It's one of the primary ways energy moves around in the world. Finally, we have work, the process of energy transfer by mechanical means. In our box scenario, the work you do on the box results in it moving across the room. The energy isn't lost, it's just changed form. Applying the first law to various processes from combustion engines to refrigerators gives us a powerful tool to understand and predict how these systems behave. It allows us to design more efficient machines, harnessing the law for our benefit. The first law of thermodynamics, therefore, is a testament to the conservation of energy. Ever wondered why your coffee cools down to room temperature? The answer lies in the second law of thermodynamics. The second law introduces us to a fascinating concept called entropy. Entropy is a measure of disorder or randomness in a system. Think of it as nature's tendency to mix things up. When your coffee cools down, it's because heat is spreading out and increasing the overall entropy of the room. Now, let's talk about heat engines and refrigerators. A heat engine, like the one in your car, takes in heat and produces work. It does this by exploiting the flow of heat from a high temperature source to a lower temperature sink. A refrigerator, on the other hand, does the opposite. It uses work to pump heat from a cold place to a hot place. So how efficient are these machines? The second law tells us that no heat engine can be 100% efficient. There will always be some heat lost to the surroundings, increasing the entropy. The most efficient engine imaginable is the Carnot engine, which operates in a theoretical cycle called the Carnot cycle. The Carnot cycle involves two isothermal processes and two adiabatic processes. It's reversible, meaning it can run forwards or backwards with no change in entropy. But in the real world, no process is truly reversible. There's always some entropy generated, leading to irreversibility. This brings us to a crucial point about the second law of thermodynamics. It provides us with a direction of time. It explains why we can remember the past but not the future, why eggs scramble but don't unscramble, and why, eventually, all stars will burn out. So next time you're enjoying a hot cup of coffee, remember it's not just a drink. It's a demonstration of the second law of thermodynamics in action, a law that highlights the inherent irreversibility of processes and the relentless increase of entropy in the universe. The second law of thermodynamics, in essence, dictates the natural direction of processes. Thermodynamics isn't just about laws and principles. It's also about cycles and processes. Let's start with the four fundamental thermodynamic processes: isothermal, adiabatic, isobaric, and isochoric. Each of these processes represents a different way in which a system can exchange energy with its surroundings. In an isothermal process, the temperature of the system remains constant. Picture a hot cup of coffee equalizing with room temperature. Next, we have the adiabatic process, where no heat enters or leaves the system. Imagine a well-insulated container where the energy changes are due to work done on or by the system, not heat exchange. The isobaric process occurs at constant pressure. Think of a heated gas in a piston, where the gas expands doing work, but the pressure remains constant. In an isochoric process, the volume of the system stays the same. This is like heating a gas in a sealed, rigid container. Now, let's visualize these processes. We use PV and TS diagrams, where P stands for pressure, V for volume, T for temperature, and S for entropy. These diagrams are like maps guiding us through the state changes in a thermodynamic process. For instance, on a PV diagram, an isobaric process is a horizontal line, while an isochoric process is a vertical line. On a TS diagram, an isothermal process is a horizontal line, while an adiabatic process is a curved line. These processes aren't isolated events. They often occur in a sequence, forming a cycle. In thermodynamic cycles, the system undergoes a series of processes that return it to its initial state. These cycles are at the heart of many engines and refrigerators. For example, the Rankine cycle used in steam power plants consists of 4 stages: pumping, heating, expansion, and condensation. Each stage is a different thermodynamic process, and the cycle repeats, converting heat into work over and over again. Understanding these processes and cycles is crucial for many engineering applications. Thermodynamics doesn't stop at pure substances. It extends to mixtures and solutions as well. Just as we have phase diagrams for pure substances, we have them for mixtures too. These diagrams illustrate the equilibrium between phases, whether it's a solid, liquid, or gas, at different temperatures and pressures. Now, let's talk about transitions. Phase transitions, to be precise. They describe the change from one state of matter to another, like from a solid to a liquid during melting. These transitions are governed by the ideal gas law, which provides a simple way of predicting the state of a gas. But remember, this law is ideal. In reality, gases don't always behave ideally, especially under extreme conditions. That's where real gas laws come into play. Next, we have saturation properties, which define the point at which a substance can no longer absorb or dissolve another substance. And phase equilibrium, that's the balance between opposing phases, like the balance between evaporation and condensation in a closed container of water. Moving on to mixtures, we encounter the Gibbs-Duhem equation and the phase rule. The former helps us understand how the chemical potential of a component in a mixture changes with composition. The latter, however, guides us on the number of variables we can independently change in a system without disturbing the equilibrium. And let's not forget Raoult's and Henry's laws. Raoult's law tells us that the vapor pressure of a component in a solution is proportional to its mole fraction. Henry's law, on the other hand, gives us the relationship between the partial pressure of a gas in the atmosphere and its solubility in a liquid. Finally, we have phase equilibria in mixtures, which describe the conditions under which different phases of a mixture can coexist in equilibrium. It's all about balance in thermodynamics, isn't it? Thermodynamics hence provides a comprehensive picture of the behavior of matter, be it pure substances or mixtures. From power plants to air conditioners, thermodynamics is everywhere in engineering, but it also plays a crucial role in sustainability. In the realm of engineering, thermodynamics is the invisible force that shapes our world. In chemical engineering, it helps us understand and predict how substances will react, enabling us to design processes for everything from brewing beer to manufacturing pharmaceuticals. In mechanical engineering, thermodynamics is the lifeblood of machines. It governs how energy is converted from one form to another, guiding the design of engines, turbines, and refrigeration systems. In aerospace engineering, thermodynamics helps us conquer the skies, powering jet engines and even rocket propulsion. Even in the world of electrical engineering, thermodynamics is at work. It governs the operation of thermoelectric generators, devices that convert heat directly into electricity, and is essential in understanding the efficiency of power generation and transmission. But the role of thermodynamics extends beyond engineering. It is a key player in the pursuit of sustainability. As the world grapples with the challenge of climate change, thermodynamics offers a roadmap to a more sustainable future. At the heart of this is energy efficiency. Thermodynamics teaches us that every process has a limit to its efficiency, known as the Carnot efficiency. By striving to approach this limit, we can reduce energy waste and lessen our impact on the environment. Thermodynamics also underpins renewable energy systems. Solar panels, wind turbines, hydroelectric plants all operate based on principles of thermodynamics. These systems harness natural energy flows, converting them into usable forms of power with minimal environmental impact. Moreover, in the field of environmental engineering, thermodynamics aids in the development of technologies for pollution control and waste management. From designing more efficient waste-to-energy plants to developing methods for carbon capture and sequestration, thermodynamics is a crucial tool. Therefore, thermodynamics is not just a scientific principle, but a key player in our pursuit of a sustainable future. As we move into the future, thermodynamics continues to evolve and adapt, finding new applications and challenges. Recent advances have seen thermodynamics playing a crucial role in cutting-edge fields like nanotechnology and biotechnology. The principles of heat, energy, and entropy are now being used to understand and manipulate the tiniest particles of our world, leading to breakthroughs such as nanorobots and targeted drug delivery systems. In biotechnology, thermodynamics helps in understanding complex biological systems and phenomena, from the workings of cells to the process of DNA replication. Thermodynamics is also paving the way in understanding non-equilibrium systems, which are systems not in a state of thermodynamic equilibrium. These systems, such as the Earth's climate or the human body, pose unique challenges, and understanding them could lead to significant advancements in various fields. So, as we continue to explore and understand the universe, thermodynamics will undoubtedly be at the forefront of our scientific and engineering endeavors.